Look at this device. It's called MOXIE, and it was sent to Mars to do one specific job: pull carbon dioxide out of the Martian air and turn it into oxygen. It represents our primary approach to surviving off Earth. We view other planets through a heavy biological bias. We assume the largest hurdle to living on Mars is securing something to breathe. But a fixation on oxygen ignores the physical reality of the environment itself. If you were to step onto the Martian surface without a pressure suit, a lack of oxygen wouldn't be the thing that kills you. The atmospheric pressure is so low that the water in your blood would boil, while the negative 120 degrees Celsius temperatures would simultaneously freeze your body. The air on modern Mars is 96% carbon dioxide and only about 1/10 of 1% oxygen. Trying to fix that equation by generating more breathable air is like trying to thaw a frozen ocean with a match. It fails to address the missing thermal mass required to keep water and humans in a liquid state. Whether an atmosphere is viable is determined by its energy balance and its heat capacity. It is a strict problem of thermodynamics, not biological preference. If we design our space missions solely around the production of oxygen, we fail to solve the planetary and habitat physics actually required for survival. We can call this the oxygen fallacy. It is the persistent belief that the presence of oxygen is the primary driver of habitability. To engineer a functional living space in a hostile vacuum, we have to master two distinct environments. First, a global planetary climate capable of trapping heat and sustaining liquid water. Second, the heavily controlled, closed-system environment of a human habitat. The macro problem spans the entire rocky surface. This is the global scale of planetary physics. Then there is the micro scale, where we attempt to bottle an atmosphere within the tight confines of a spacecraft or an altitude chamber. Understanding how to survive in either scenario requires examining the Ramirez models for global planetary warming alongside the Huggett models for closed-system safety. This image shows a deep, winding valley network carved into the Martian crust. It provides undeniable geologic evidence that sustained, flowing liquid water existed on the surface in the deep past. Climate models run into a severe physics barrier here. Around 3.8 billion years ago, when these valleys formed, the sun was roughly 25% fainter than it is today. Based on solar radiation alone, early Mars should have been a completely frozen block of ice. Early attempts to explain the warming assumed a thick, high-pressure carbon dioxide atmosphere. But at 2 to 3 bars of pressure, carbon dioxide begins condensing into surface ice. Worse, the dense gas particles deflect incoming solar particles back into space, a process called Rayleigh scattering. Because of that severe scattering and surface condensation, standard 1D and 3D climate models cannot push the mean surface temperature above 230 Kelvin using just carbon dioxide and water vapor. The existence of these valleys established that a secondary warming mechanism was necessary to bypass the radiative limits of a pure carbon dioxide atmosphere. Planetary scientists have proposed a highly specific solution. They theorize an early, heavily reducing atmosphere filled with hydrogen outgassed directly from active Martian volcanoes. This relies on a mechanism called collision-induced absorption. When a carbon dioxide molecule physically collides with a hydrogen molecule, the impact creates a temporary dipole. In that fraction of a second, the paired molecules trap escaping infrared radiation. This process effectively traps outgoing radiation. Thermodynamic calculations demonstrate that mean surface temperatures can rise above freezing with as little as 1% hydrogen and just 0.55 bars of carbon dioxide. Researchers process these variables through a Mars energy balance model. The planet is divided into latitudinal bands, calculating heat diffusion from the equator. Applied to this grid, the model predicts a massive liquid ocean across the northern lowlands, actively transporting heat globally. As the atmosphere warms the crust and melts the accumulated ice, the planet's overall albedo drops. Darker soil and liquid water absorb more solar radiation, accelerating the warming in a positive feedback loop. This chart shows the exact Manabe-Weatherald humidity profile used to calculate these conditions. The solid blue line tracks how relative humidity linearly decreases as atmospheric pressure drops with altitude, ensuring the model maintains a precise water-vapor balance. The energy required to melt a frozen planet was supplied entirely by the kinetic collisions of reducing gases. On a macro scale, oxygen was completely absent and thermodynamically irrelevant. When we zoom in from a planetary atmosphere to the micro scale of a human habitat, the physical requirements invert. We pump in high concentrations of oxygen to satisfy human biology and instantly turn a metal cylinder into a high-energy physics experiment. In an open, terrestrial environment, a fire vents its heat and toxic byproducts safely into the sky. In a closed aerospace system, the heat and pressure have an absolute physical boundary. They accumulate. Chamber fires obey a strict, mathematical equation. The rate of the fire's growth is proportional to the flame volume, resulting in exponential growth limited only by the initial supply of fuel and oxygen. The reality of this exponential curve was recorded during the Apollo 1 command module fire in 1967. Within 20 seconds of ignition, the internal pressure spiked by 20 psi, and the titanium chamber physically ruptured. This graph plots the precise pressure-time history of that cabin fire. The data forms a straight line on this logarithmic chart, mapping the violent, exponential pressure spike that destroyed the module. At the exact moment the pressure breached the hull, less than 10% of the total oxygen in the cabin had been consumed. The system didn't run out of air. It simply couldn't contain the ferocious rate of energy release. Inside a sealed box, oxygen ceases to be a life support mechanism. It is the primary oxidizer for a thermodynamic explosion. As oxygen behaves so violently in a closed loop, why don't fires spread exponentially every time a spark is struck here on Earth, breathing 21% oxygen? The variable that controls this is called C'(P). It represents the heat capacity of the atmosphere per mole of oxygen. You can think of it as the thermal sponge of the gas mixture. This chart shows the rate of flame spread against that heat capacity. Notice the strict downward angle. As you mix in inert diluent gases like nitrogen or helium, the heat capacity increases, and the flame spread rate drops to near zero. Earth's atmosphere is composed of 78% nitrogen. When a spark occurs on the surface, those inert nitrogen molecules act as a massive heat sink, absorbing the thermal energy before it can vaporize surrounding fuel. In an oxygen-enriched habitat, that thermal sponge is completely removed. The heat capacity is severely reduced. A single spark instantly vaporizes any material it touches, turning the loose thread into a cascading wall of flame. This table classifies the safety of atmospheric mixtures based directly on that heat capacity ratio. Any gas composition with a C'(P) below 10 is categorized as an extreme hazard, guaranteeing catastrophic fire propagation. Safety in an aerospace environment isn't achieved by maximizing breathable oxygen. It requires calculating the exact ratio of inert diluent gases needed to suppress raw thermal energy. The oxygen fallacy is rooted in our biology. We need it to survive, but the physical laws of habitability demand precise thermodynamic control over how heat is trapped and released. On the planetary scale of ancient Mars, maintaining a warm, wet environment required an atmosphere saturated with volatile reducing gases. Oxygen played zero role in preventing the oceans from freezing. On the micro scale of a habitat, keeping an astronaut alive requires burying the necessary oxygen in a dense layer of inert gases. Without that buffer, the atmosphere will tear the structure to pieces. We are left with an engineering paradox. To save a frozen planet, we required the aggressive heat-trapping physics of reducing gases. To save an astronaut in a sealed metal cylinder, we require the heavy, dampening weight of inert sponges. The air we breathe is a complex thermodynamic engine. If humans are going to engineer a long-term presence on a world like Mars, we have to stop thinking strictly as biologists and start thinking like thermal engineers.